All right, in this video, we're going to take a look at an example where we want to construct a confidence interval for a mean, in this case, the mean weight of all babies that were born in North Carolina in 2004. And we don't know anything about the population other than we actually have a really large sample in this data set, NCBirths2004. So we don't know what the population mean is, obviously, or we wouldn't want to estimate it. And we don't know what the population standard deviation is either. So in that situation, when we don't know what sigma is, our confidence interval for the mean is going to be found by taking the mean of the sample and then going T alpha over 2 times the standard error, or at least our estimate for the standard error of the sampling distribution. We're going to subtract that from our sample mean for the lower estimate, and we're going to add that to our sample mean for the upper estimate. Okay, so when we've got a really large data set such as this one, we're going to really want to use R to calculate these values. So the first thing that I might want to make a note of here is we are finding a 99% confidence interval. So what that means, these values of minus T alpha over 2 and T alpha over 2, the area in the middle should be the 99%. So that means we're missing 1% of the area. And half of that 1%, in other words, 0.005 is over here, and the other half of that 1% is over here. So one way that we can find out what T alpha over 2 is would be to use this Q norm function. In this case, it's QT because we're working the T distribution. And we would want to calculate what is the total area, say, to the left of T alpha over 2. And that's going to be the 0.99 plus the 0.005. So that's actually going to be 0.995. And the next thing we would need to enter would be our degrees of freedom, which are going to be n minus 1. So we're going to use R to calculate all of these values. So I am going to flip over to a terminal, R terminal that I have open. Okay, so here we are with R, and we've got the first thing we want to do is load up resample data library. And so we're going to be working with the data set North Carolina births, in particular the variable weight. So I'm just going to pull that off and create a data vector called weight. So I've already loaded up the resample data. Now I've created a vector called weight. And so if I want to calculate my sample mean, then I just calculate the mean of weight. And we can see that the sample mean, in this case, is 3,448.26 grams. So I'm just going to record that over on the slide. And next would be the standard error of the sampling distribution. So I can do this in 2 steps. I'm going to calculate the standard deviation of the weight. I don't need to do that intermediate step, but that's how we would do it. And then we would get the standard error by taking the standard deviation from the sample and dividing by the square root of n. So that's what square root, and n now is the length of the vector weight. So maybe since we're going to use this a couple of times, I'm going to just create that over here. So n is going to be the length of weight. So that's how many things we have in our sample. Oops. And then over here, this is simply going to be the standard deviation of the weight divided by the square root of our sample size. And let's see what the standard error is. So that gives me a standard error, or at least an estimate for the standard error which is, we'll say that's 15.35. And then we want to find out what the cutoffs are. So the T alpha over 2 values. So I'll just call this T alpha, maybe TA to make it simple. And here we're going to use this QT function where, recall, we wanted for 99% confidence interval, the area to the left of this value to be 0.995. I don't like this here. So we've got TA is equal to the 0.995 quantile for the T distribution that has n minus 1 degrees of freedom. Okay, where here n was our sample size. And we can see what that is over here. And that gives us an approximate value of 2.58. And that would give us all of the values that we would need to plug in. So then for our lower cutoff, we would take our sample mean, which is samp mean, and then we're going to subtract the lower cutoff TA times the standard error. Okay, so this TA times the standard error, that's actually our margin of error. And then for the upper cutoff, we're going to do the same. We're going to take our samp mean, and now we're going to add TA times the standard error. And so now let's see what we get for our lower limit is 3,408.6. And our upper cutoff is 3,487, we'll say 0.9. So that gives us our 99% confidence interval would be from the 3,408.6 up to 3,487. And so what this tells us is there's a 99% chance the interval from 3,408.6 grams up to 3,487.9 grams has a 99% chance of containing the actual mean weight of all babies that were born in North Carolina in 2004. So one last thing that I want to just talk about before I go back over to the slide is there was this step over here where we wanted to calculate what is the multiple that we're multiplying by the standard error. In other words, what was that T alpha over 2 value? And I alluded to earlier that we could use T distribution table to calculate these. So let's kind of see how we could calculate this command that I've highlighted in blue using the T distribution. So we want to find the cutoff so that the area to the left is 0.995. We had a 99% confidence interval. So this is a table that is from your textbook. So you can check out the back of your textbook. You have something similar. And so right now we're using the T distributions. Notice that up here. And we want to construct the confidence interval. And so what we would need to know is how many degrees of freedom do we have? And this table goes up to, say, 500 values. And let me kind of recall how big our sample was. I think it was quite big. Yeah, so our sample had over 1,000 observations in it. So that would put us at like the infinity mark over here. And so what I would do is say we wanted a 99% confidence interval for something that had approximately an infinite number degrees of freedom. And so that comes out to be 2.576. And that's exactly what we got from when we did the QT inverse operation. So here, what you can do with this table is look up the degrees of freedom, which should be n minus 1, and then come down the column corresponding to the confidence level. And pretty much these are the most common confidence levels that are used. Then you would come down that column and stop when you hit the right degrees of freedom. So you could use a t-table if you like. You're welcome to use the qt command in R. And one more thing that I wanted to do in R, which is we could do the full test in R. So let me open R up again. By using this ttest command. So you certainly don't need to do all of the work I did above. Instead, you could just say, we're going to do a t-test using the data from weight, and I'm going to set a confidence level. In this case, I want 0.99. And this last command, $conf, means we're not actually doing a hypothesis test. I want to use this to construct a confidence interval. So when we re-look at hypothesis tests, we'll see what happens when we don't include that last $conf. But since we do want a confidence interval here, that's what this end of the argument is. And when we run this, we should expect to get similar estimates from our work above. And you can see here, we get exactly the same output, that it goes from 3,408.6 to 3,487.9. So let me just say that you could just enter this one command, and that's fine. That would calculate the confidence interval. It might not hurt to do it in bits and pieces, just so you understand how you could construct this yourself. So let's kind of wrap up this example by coming back to the slide that we started with. And so we wanted to approximate we wanted to approximate the mean weight of all babies in North Carolina with a 99% confidence interval. So I was just recording some of the results that we were getting from R. We used the qt command, and we got that T alpha over 2 was 2.58. This is exactly what you would get from the T distribution table. We found the standard and estimate for the standard error. This was our sample mean. And then using the formula that we have up here, we got the following estimate. And so here we would say that there's a 99% chance the interval from 3,408.6 to 3,487.9 grams contains the mean weight of all babies born in North Carolina in 2004.